Welcome! In this video, I will show you how to determine the connection formulas in the WKB or semi-classical approximation for the case where we have a downwards sloping potential. Now, we have already done this procedure for the upward sloping potential, and I will assume that you have watched it because although the procedure will be basically the same, I will try to go at a bit of a faster rate now than I did in that other video. So if you haven't watched it and any of this doesn't seem to, or you don't quite understand it, I do recommend that you go watch it. I will put the link in the description. So this, by the way, is also problem 8.9 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. The problem states, derive the connection formulas at a downward sloping turning point and confirm the equation that is in the book. So what we now have to do is basically see the situation that we have right here. So we have this downward sloping potential that I drew here, and at some point, since it is down sloping, right, it will go from having energy greater than that potential, so smaller, to have an energy greater, because the potential is decreasing. So we will have one region here, which is the non-classical region, non-classical, and we will have another region, which is the classical region. Now, notice the first difference with what we had previously. In the case where it was upward sloping, right, we had something like this. In that case, the classical region was here and the non-classical region was there. They were swapped. Now, exactly the opposite, right? So that is important to note. Now, this turning point could happen anywhere. I'm going to, instead of calling it some, I don't know, x1 or x2, I'm just going to call it 0. Again, because we can simply shift our axis so that this makes sense. Now, just to remind what the procedure is, what we want to do is, since the WKB procedure, it doesn't work at this point where the energy is the same as the potential, it doesn't work because both expressions for our wave functions, the WKB approximation, they go like 1 over the square root of the momentum. And the momentum is square root of 2m e minus v or v minus e. But since they're going to be the same, it blows up. It goes to 0, and this thing is 1 over 0, and that just doesn't work. So for that reason, we will come out with this new region, which we will call the patching region, and we will find a wave function called the patching wave function. And what we will want to do is that as x becomes greater and greater, this patching wave function will have to turn into, right, asymptotically, to the wave function in this region. Maybe let's call it psi3. And similarly, as x becomes more and more negative, we want our patching wave function to basically turn into the wave function that the WKB approximation gave us for that region. So that is what we want to do, just as we did in the previous video. So how do we find this wave function? Now, it will be basically the same as before with some minor differences. So first of all, let's approximate our potential. Since we can zoom in, right? If we zoom in enough, whatever this potential is, it's going to look like a straight line. So we can approximate our potential as long as we are sufficiently close to this turning point. We can approximate it as the energy, and then we can add this slope that our potential has, v prime, evaluated at 0. Now you have to consider this v prime, so v prime of 0, this is negative, okay? So this is very important. So I just wrote it plus this amount, but that amount is, of course, negative. You could use a minus sign, but I want to make sure that the notation looks like the same result we got in the previous case. Okay, so now we want to solve the Schrodinger equation for this potential. So let me plug everything into the Schrodinger equation. So plus the potential of the patching wave function, this is equal to the energy times the patching wave function. Now, of course, instead of this potential, we write E times the patching wave function plus V prime of 0 x times the patching wave function. So from here, we can see that the second derivative of our patching wave function with respect to x will be, let's see, so this part will be negative, but there's another minus sign, so we get positive 2m divided by h bar squared times v prime of 0 x psi of p. So now we have something quite similar to what we had before. We have this thing right here, and we can now call it alpha, but there is a slight issue, first of all, with the notation that we had before. But what I would like to do right here is say, okay, keep in mind that this potential is negative. So what we can do is write this as the absolute value of the potential and put a minus sign in front. So by doing that, we can now define alpha cubed, right? Quite similar to what we did in the previous case, 2h bar squared, and this is v prime of 0, but of course in absolute value. So by doing that, we get that this thing right here is simply minus alpha cubed times x. And now what we can do is, once again, similar to what we did before, say, all right, so z will be alpha x. So for that reason, by using the chain rule, we will get an alpha squared here. So we get d squared psi patching dz squared and alpha squared. Again, I did this with more detail last time we did this. And then we have minus z alpha squared patching wave function. So of course the alpha squares, they just drop out. But now notice what we have here. This isn't quite what we had found previously, because previously, and by that I mean in the video with the upward sloping, right, we found this but with a plus. So what we can do is define z as minus alpha x, and then this becomes positive, of course, and there we go. So, and of course there will be no difference here because of the way that we defined this. This minus became absorbed, and this here is squared, so the minus that comes from the dx ends up canceling out. So now I'm just going to write this closer together. We found, once again, our Airy equation. And the main difference with the previous case is that now our z has a minus sign inside, and that will affect the situation very, very shortly. Now, the solution to this are the same as before, thankfully, and I'm going to recall what they are. Again, solving this is beyond the scope of any quantum mechanical course. So I will show you the results here, and eventually I will add a video on my mathematical methods of physics where I explain how to find them. So these are the asymptotic forms, right? So the asymptotic solutions, right? This time I'm not writing down the integral representations because I already discussed them in the previous video. So in asymptotic, we have two cases when z is much, much greater than 0. That's what you had seen before. However, we have to take into consideration that our z is now minus, right? So I'm going to show you the expression that we had used. And in fact, these are the overall solutions, right? So we had, in this case, 1 over 2 square root of pi, and then 1 over, or maybe let's just extend this, and then z to the 1/4, and then we have e to the minus 2/3, z to the 3/2. And let's see, then we have bi of z. This now goes as 1 over the square root of pi, z to the 1/4. And then we have, for what used to be, right, z much, basically when we have very large negative numbers, right, then we had ai was 1, or actually approximately, right, 1 over square root of pi minus z to the 1/4. And then sine of 2/3 minus z 3/2 plus pi over 4. And finally, bi of z, this goes as 1 over square root of pi minus z to the 1/4, and cosine of 2/3 minus z to the 3/2 plus pi over 4. So let me make this very, very, very clear. So in the last case, okay, so previous video, we had the situation where x and z were either both positive or both negative, okay? So basically, when x became more negative, so did z. And when x became more positive, so did z. But in this case, x and z have this minus. So as x becomes more and more negative, then z becomes more and more positive. Okay, that is very important. That's the second big difference with the previous case. And well, and the other way around, if x becomes very, very, very positive, very large, z becomes very, very, very large, negative. So that is the main difference. So even though this is valid for z very, very, very large positive, we can't get confused and use the same that we used in the other video, right? With the upward sloping case. Okay, with that in mind, we already found our solutions, right? Our patching wave function is going to be a linear combination of AI, right? These are the Airy equations of the first kind, and BI, the Airy equations of the second kind. So now what we want to do is patch them together with our new, or basically with not the new rather, but the solutions for the classical and the non-classical regions. So what was our wave function? So let's begin with the non-classical region. So let's see. So what WKB theory tells us, now let's begin by writing down the non-classical solution. So that was 1 over the square root of the absolute value of momentum, and then we had some constant d, e to the minus. Now this is the non-classical solution, so here we have this exponential that is decreasing, integral from, and now we go from x all the way to our turning point. x2 is now 0, right? And we are integrating over the absolute value of the momentum, and we use x prime so that it doesn't get confused with this x here. Okay, so that is for x non-classical, which is when x is smaller than 0, right? This is different from the previous case. And then we have the classical case, which is 1 over the square root of the momentum. And then we have two cases, or rather two parts. So some constant b, e to the I over h bar, integral from now 0 all the way to some x. And then we have momentum, and then plus some other constant, e to the minus I over h bar, integral from 0 to x, again of momentum, right? It's the same thing. And this is for x greater than 0. So now we need to patch everything together, right? We want to, the appropriate, basically go back to this condition here. As x becomes very, very negative, we want the solution in this region, which is the non-classical region, to become the same as the region, as our wave, as the patching wave function. And again, negative x mean positive z. So that means that in this first region, right, and we want to make sure to begin with this region because there's only one term there. It's going to make things a bit easier, right? So basically what we want to do is take the wave function that we just found here from the WKB, which will be the non-classical region, right? Or region 1, if you want to call it that way. Basically the region where x is smaller than 0. And we want to set this equal to the patching wave function, but in which regime? If x is negative, then we're dealing with positive z. So we're going to do it when z is very, very large in the positive direction. So we want to use this formula right there, and set it equal to the case where z is positive, very large, so basically these ones right there. However, we haven't really calculated the momentum, its integral, or the absolute value of the momentum, or any of that. So let's take a moment to calculate everything that we need related to that. So let's begin by just calculating the momentum, and we will take the absolute value later. So this is the square root of 2m e minus v. Now, what is v, right? Our potential, we already said it's going to be e plus v prime of 0 x. And v prime of 0, of course, is negative, so be careful. So this is square root of 2m e minus v prime of 0 x. Okay, so let's see, the e's cancel out. We get square root of minus 2m, and then we have v prime of 0 x. Okay, so now let's begin taking a look at our various regions. So if we are in the case where x is positive, then we have minus and a negative number, right? So let's say that we are indeed in the case where x is positive, which is a classical region. So in that case, this is simply going to be a positive number, and we can write this as 2m times the absolute value of this slope times x. Now, in the region where x is smaller than 0, which is of course the non-classical region, our momentum will be the same, but now we can put the minus into the potential again, right? So write this as 2m and then the absolute value of our potential, and then we have x, but x is going to be negative. So if we want to be able to use this, we need to use the absolute value of the momentum, which will give us a minus in there. So this will be maybe like this. So this will be square root of 2m absolute value of v prime of 0, and then times minus x. And again, just as in the previous video, we can multiply and divide by h bar squared with the objective of turning this first part right there into alpha cubed. So by doing that, we get alpha to the 3 over 2 h bar and then square root of minus x, right? That minus x, of course, ensuring that the momentum will be real, because x is always negative in this region, so we get minus a negative number, which is positive. Okay, so now let's integrate both of these amounts. So in the case x greater than 0, we integrate from 0 to x of p of x prime dx prime. And let's see, that is the result that we got. Maybe let's change colors. So we get square root of 2m, right? We can just pull all of this part out of the integral. And then we integrate simply x to the 1/2 dx, which will give us, and again, well, actually, we didn't use the alpha notation here. We should have done that. So this thing right here, just as it is underneath, this is alpha to the 3 over 2 h bar square root of x. Right, so this thing right here is h bar times alpha to the 3/2. Okay, and this integral right here, this is simple. That integral gives us 2/3 and x to the 3/2. All right, so again, I'm going a bit faster because this is something that we have already calculated in the previous video, and I don't want to repeat too much. So now x smaller than 0, this will be integral, right? This is a non-classical region. We go from x to 0, right? 0 is where we end the region, so we have to do it like this. And that is the absolute value of the momentum this time. So by doing this, we just plug this in. We get alpha 3/2 h bar, and then we integrate from x to 0 of minus x to the 1/2 dx, primes, of course. And then, well, our constants, they don't change. And this integral will become minus x 1/2 And sorry, not 1/2, but rather we have to get 2/3, because this now becomes 3/2. And then we multiply by the derivative of what is inside, which is -1. And we have to evaluate this with between x and 0. At 0, of course, the result will be 0, but at x, it will not. So this minus cancels out from the minus from integrating in the second limit. So we get minus minus, which is of course plus, alpha to the 3/2 h bar, and then we get 2/3, and then minus x to the 3/2. Okay, so with this result, we can now go back and plug it in. So our non-classical wave function for x smaller than 0 is this thing right there. So let's just begin plugging everything in. So we get 1 over the square root of h bar. Then we have alpha to the 3/4 and minus x to the 1/4. Then we have everything else. So times d e to the minus. The 1 over h bar cancels out with the h bar in the integral, or that came from the integral. So we get 2/3, and then we have alpha x. I'm just going to put them together, or rather minus alpha x. So minus alpha x to the 3/2. And this has to be equal to the Airy functions evaluated at z very, very positive, very large, very positive. So this would be 1 over 2 square root of pi, z to the 1/4, e to the minus 2/3. And actually, let me write what z is. Z is minus alpha x. So we get 3/2. And then this has to be multiplied by a, right? Keep in mind that this is the wave function that I'm considering. So we have a small a times the first kind functions of Airy, and then plus b times the second kind, right? And this z I'm going to also write as minus alpha x. Okay, so plus b divided by the square root of pi, z to the 1/4, but z is minus alpha x. Alpha right here. Wait, I just realized that I apparently didn't finish copying this case of the Airy function. I'm sorry. Z to the 3/2. Okay, that was weird. Well, anyways, copying this here, so we get e to the 2/3, and then z to the 3/2, which is minus alpha x to the 3/2. So if we want these things to be equal, we need the exponents and what is alongside the exponents to be equal. But there is nothing on the left-hand side that has this positive exponent. So b has to be equal to 0. So that is one condition. And the other condition, of course, comes from setting this part equal to this part. So that means 1 over h bar, alpha to the 3/4, minus x. I guess I could have put the alpha in there, times d. So let me put the d there. And a divided by 2 square root of pi minus alpha x to the 1/4. Now I can write this alpha to the 3/4 as alpha to the 1/4 times the square root of alpha. And by doing that, I can get rid of this and this with this. Now let's solve for a just as we did in the previous video, because that way we can then just compare a in each one of the regions, because both regions have different constants, right? Our goal is to get rid of this d, b, and c, right? We basically want to apply border conditions, as I mentioned in the previous video. So by solving for a, we can easily connect b and c to a, and also d to a, and then connect them all to each other. So a, small a, will be, let's see, so 2 times the square root of pi over alpha h bar, and then we multiply by d, and that's it. Yeah, there's nothing else. Okay, there we go. This is another condition. Now we do the exact same thing, but for this other region. So basically now for psi classical, right, which is basically when x is greater than 0, we want this to be equal to the patching wave function evaluate it, but now if x is positive, this is when z is very, very large and smaller than 0, basically negative. So in that case, let's now write down what our wave function is. So the classical wave function, this will be 1 over the square root of the momentum, which is square root of x, square root of alpha. I'm going to now separate the alpha, right? Alpha to the 3/4 is square root of alpha times alpha to the 1/4, but I'll just put alpha and x together right away. Okay, so alpha x to the 1/4. Just making sure that I didn't make a mistake. Yeah, okay. And now we have times b, e, and this is to the I over h bar times 2/3 h bar alpha x to the 3/2. Again, the h bars cancel out, so we end up with 2/3 I. And then we have the same thing, but the exponent will be negative, so we can just copy it quickly. Alpha x to the 1/4 and e to the minus 2/3 I alpha x to the 3/2. And this has to be equal to our patching wave function in the region where z is very, very negative. Now, these were our solutions for the patching wave function, right? Considering that we have to take a linear combination of them. But we know that small b is equal to 0. So we don't need to worry about this part at all. So we only take this times small a. Now, let me copy it. So it is, let me see, a divided by the square root of pi. And then we have minus z. But z is minus alpha times x. So we get alpha x to the 1/4. Then we have sine of 2/3 minus z again. So we get alpha x to the 3/2 plus pi over 4. Now, if we want to compare both sides, we have exponent, exponent, sine. So we need to either turn exponents into sines or sines into exponent. Going from sine to exponent is much easier in this case, so let's go for that. So considering that sine of x is e to the ix minus e to the minus ix divided by 2I, we can now simply write this as e to the I, and what did we have inside? We had 2/3 alpha x to the 3/2 plus 4 pi over 4. But we can write this as e to the I pi over 4. Then we got minus e to the minus I 2/3 alpha x to the 3/2. And then we got e to the minus I pi over 4. And all of this divided by 2i. So now we are in a position to start equating everything that is accompanying the positive exponent and the positive exponent here. So let's begin with that. So we get b divided by the square root of h bar alpha times alpha x to the 1/4 has to be equal to a divided by 2i square root of pi alpha x to the 1/4. And of course, let's not forget about e to the, let's see, we are equating b and a, so it has to be a positive ei pi over 4. So now when we isolate a, right, we want to have something a is equal to, some b, and eventually we want to have it right as we had the d, right? So we want to isolate a, that is the point. So to do that, well, these parts cancel out and we get 2ib, and then the exponential will be negative, right? We need to multiply by its inverse. And then we have square root of pi divided by h bar alpha. Okay, so here we have another little result. And now equating the negative part, right? So basically this and this to this, so the negative exponential, we get c divided by, now of course these parts will cancel out, so I won't bother writing them down. H bar alpha has to be equal to a, so minus a e to the minus I pi over 4 divided by 2I square root of pi. Now from here we can find a. So a, we multiply by 2I, we have a minus sign, so we get minus 2I c e to the positive I pi over 4, and then square root of pi h bar alpha. So did I consider everything? Yes. So here we have it. We now have a formula for B, C, and A, and also D in terms of each other. Now, just as a reminder, A is to this. I'm copying the one for D so that I can see everything clearly. Okay, so now we want to plug in this into each one of those, because when we do that, we will have B and C in terms of D, and we can then combine everything. Whoops, I didn't mean to do that. We can then combine this expression into one, because the constant in front of them will be the same, which is the same as this one, which we could find by normalization if we needed it. Okay, so plugging it in, we get, so we have 2 square root, but well, the square roots will cancel out, right? This will cancel out with that, so I won't bother. 2d is equal to 2I be to the minus I pi over 4. And from here, I want to solve for b. So of course, I multiply by I divide by 2. So I get minus I, right? Because there will be a minus sign here once I multiply by I. And then e to the positive I pi over 4, d is equal to b. And I'll just put it like that. And now similarly, now I'll plug it into the equation for c. So I get 2, which will actually cancel out as well, right? So this and this cancels out with this and this. So I get that d is equal to minus ic e to the I pi over 4. So from here, I can find that c is equal to, if I multiply by I, this becomes I squared, which is minus 1, which cancels out with this minus. So I get id e to the minus I pi over 4. Now, I can plug all of this into this little formula here. And notice, right, that this is the WKB formula, okay? And why do I mention it like that? Because the WKB formula is valid for the regions that are not the patching region, okay? So we don't really need or even want to write down the momentum like we did before, because this is just for the overall expression, right? The general expression. Okay, so now let me rewrite this, but with what we found B and C to be. So, or rather B and C, sorry. Okay, so it is minus I e to the I pi over 4 times D, and now the exponent that is already there, so I times the integral, right, I over h bar times the integral from 0 to x of the momentum dx, and then plus what we had for C, which is id e to the minus I pi over 4, and then the same exponential that we had before, right? Minus I over h bar, integral from 0 to x, momentum, x prime, dx prime. And all of this is valid for x greater than 0. So now let's factor out d. That is the great, amazing achievement that we have. So we can factor it out. It doesn't look good. I'll just do it like this. And now notice that we have some exponential with a positive exponent, but negative here at minus, and then the same exponent, but negative. So my point is that this looks like a sign, right? Just as we did in the previous video. So let's factor out a minus sign. And then this looks even more like a sign because we have e to the I something minus e to the minus I something. However, we have this I here, so let's factor it out, right? And this is twice the sign, 2 times I times the sign, right? Because sine of theta is e to the I theta minus e to the minus I theta divided by 2i. We only have the exponents, so what we have is 2i times sine. So this thing here, whoops, I didn't mean to erase the x smaller than 0. So what we have there is 2i times the sine of, and then we have what was inside. It was pi, or actually let me put the pi over for later. So this was 1 over h bar integral from 0 to x p of x prime dx prime plus pi over 4. And the i's that are here will give us a minus 1, which will cancel out that negative. So this is basically 2d. And there we go. This is our result. We can now just move our x-axis and say that our turning point is not necessarily at 0. It could be, but more generally, we can call it x2. Well, and of course, keep in mind that since we moved our turning points, now our two regions are defined, right, by when we are to the right or to the left of the turning points. So of course, we also needed to change that category there. So there we go. These are the connection formulas. So I hope that this was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.